So this is an example of how the key value store scales out to give massive throughput capacity. And so in this case, instead of having just one switch, we have multiple switches in a data center, typically at the top of the rack. And we have not just one, but multiple key value stores that are installed in the servers. And so typically in Microsoft data centers, for example, that for every 2 sockets that there's a FPGA card that's installed on a mezzanine. And so you have multiple FPGA cards in the rack that are connected directly to the top of rack switches. And we have, in this case, multiple sensors that are streaming data into the key value store. And they can be writing this data in parallel and having redundant data that's being written to multiple key value pairs so that even failures in data center don't affect the quality of the data. It's redundant. So at Algo-Logic, we've done benchmarks of implementing key value stores with different types of software and hardware. And so the most traditional way of building a key value store is to write a user application, run it on top of a Linux kernel, and run that on a standard Intel i7 or Xeon with a NIC. And so in this case, your request comes in over the network, comes in the NIC, goes through the Linux kernel, goes to the application, the key value store retrieves the value with a key and sends it back down the network stack, and it goes back to the host. A faster way of doing this is by having kernel bypass. And so using, for example, the DPDK library from Intel, you can have a processor queue that's polling on the data that comes in off Ethernet to deliver it to a waiting application on a receive queue that processes the message, performs the key value pair update, updates the message, and then sends that message back out. So the DPDK runs on the same hardware as the socket I/O, but it does it faster because it bypasses the Linux kernel. Instead, it dedicates hardware IP cores so that, in this case, multiple IP processors are running to receive the data, process the data, and send it back out. The FPGA takes a different approach. On the FPGA, we can offload this entire key value store application into the logic on this FPGA. And so in this case, packets come in, we parse the packets, we decode the headers, we perform the key value extraction, and we go to our search engine to resolve the key value pair. We package that back up into a packet and send it back out over Ethernet. So this is exactly the same result that we started with in all 3 of these applications of implementing a key value store. But in this case, the difference is that the key value store was resolved by the packet coming in from the network port, going to the FPGA, reading out of local memory that's on the FPGA card, and going right back out the wire. And so this gives us a very fast way to process data. So looking at the throughput of how much data that we can process is that typically we have a graph that shows the percent of packets that get processed. And so 100% means we're processing all the data. And then we look at how much we load it. And so on this scale, this is a log graph, starting with 1 million packets per second, going to 10 million packets per second, going to 100 million packets per second. And so what's happening is that as we have software that's processing packets, at some point, once you get to a few million packets per second, is that it drops off. Is that the CPU core can no longer keep up, and so packets begin dropped. And so instead of processing all of the packets 100%, you start processing 50% of the packets with just a few million packets per second. DPDK does better because you've dedicated multiple cores to receive the packet, process the key value lookup, and write it back out. And because there's no overhead from an operating system, DPDK gives you almost an order of magnitude better throughput because instead of dropping packets at 10 million packets per second, you can get almost to 20. The FPGA, however, is a little bit different. Is that because the hardware data path has been engineered to take line rate data, is that it doesn't drop packets. Is that it's able to keep up with the full line rate 100% up until you're sending data in as fast as it can go. And so that fully loaded is that the FPGA can process packets, and for this application we can go up to 40 million messages per second on a 10 gig link and still not have any packet loss. So one of the most exciting parts of doing the key value store is looking at the latency. And so the latency, if you do key value store with a CPU, with a Linux kernel and software, gives you the worst latency and the worst jitter. And so by that, what we see happening here is we have the distribution plot of the latency. And so this blown up is showing us that we have an average latency of about 41 microseconds for software sockets to do the key value store, but we have a pretty wide jitter range. So this is about 10 microseconds of jitter with a very long tail. This actually goes even further than what's shown on the graph, which means that some packets can take as much as 100 microseconds to process if the kernel's busy. And so if you're doing a real-time application and some packet responses don't come back for tens or hundreds of microseconds, this can delay and make your system not be real-time. So using the kernel bypass helps, is that by avoiding the operating system and just processing all the packets directly on the CPU cores, that you can much reduce the latency and the jitter. And so we see from going from about 41 microseconds down to about 6 microseconds, single-digit latency, with the bypass of the kernel, is that we can get a much less latency. So this is, and the jitter, you can see this is almost an impulse function, although there's a few packets that get processed a little faster and a little bit later. And so there's cache line effects that happen on a CPU system. Sometimes multiple events come in at once, and so the CPU still has to sequentially process these events, and so there is still some jitter, but a big improvement in latency. Now, going one step further to the FPGA is that going from single-digit microseconds down to a half a microsecond is that we're able to, by processing all the packets in hardware, that we can make sure that all of the offer load gets processed deterministically with a latency that's about 1/10 of the latency of kernel bypass and about 1/100th the latency of the software sockets. And so with the key value store in the FPGA, that not only is the latency under half a microsecond, but it's very deterministic. There's almost no jitter. It's a perfect impulse function, and so all the packets are being processed at that same instant of time. So in summary, this key value store, by doing it on the FPGA, is that we can significantly lower the latency. So we're getting a 14 to 88x improvement over the optimized DPDK in traditional Linux software. We're getting a massive increase in throughput by about a 10x improvement by having it offloaded to the FPGA, and about a 13 to 21x less power because the data is only moving into the FPGA and back out. So there's savings in latency, throughput, and power by running this on the key value store.